Hi everyone. In this lesson, we'll learn the most popular regression algorithms. Linear regression. Linear regression, a supervised learning method, tries to predict targets with continuous values. However, with a little trick, it can also be turned into a classification method. Now, we will look at its capabilities. Let's get started. Classification methods focus on determining the best boundary that separates groups from each other. By accepting that the data consists of different groups. Unlike classification, in regression methods, data points are considered as a single group and the best graphic representation of them is tried to be found. Linear regression, by formal definition, is a statistical method that aims to predict a dependent variable using an independent variable. Y equals W0 plus W1 times X plus E. Here, W0 and W1 represent weights of the equation. X is independent variable or input features in dataset. E is unpredictable error. And Y is dependent variable or desired value in dataset. In this lesson, we will learn to find weights of the equation. Evaluation of a linear regression model is crucial for understanding its performance and accuracy. We will focus on two key metrics: R-square and mean squared error. R-square measures how much of the total variance in the dependent variable is explained by the independent variables. It ranges from 0 to 1. While 0 means that the model does not explain any of the variance in the dependent variable. 1 says the model explains all of the variance in the dependent variable. A higher R-square value indicates a better fit of the model to the data. Mean squared error, in shorter MSE, measures the average squared differences between the predicted and actual values. Unlike R-square, which is a proportion, MSE is an absolute measure of fit. When MSE is 0, it means perfect predictions with no error. Higher MSE values indicate larger errors in the model's predictions. MSE is calculated by squaring the error for each prediction, summing these squared errors, and then averaging them. It provides insight into how close the model's predictions are to the actual values. Now let's take a quick look at how to do the comment on a small example. When we solve the example on the left with a Python code, we get the solution on the right. But what do the R-squared and MSE values we get here mean? The R-squared value of 0.731 indicates that the model explains 73.1% of the variance in the dependent variable. This suggests that the model is quite strong and explanatory, meaning the independent variables have a significant impact on the dependent variable and that the model generally performs well. The MSE value of 23.30 indicates that there is some error in the model's predictions. To evaluate whether this error is acceptable, consider the range of the predicted variable's values. For example, if the predicted values are around 1000 units, an MSE of 23.30 would be quite low and acceptable. However, in this example, the predicted values range from 10 to 40 units. Then an MSE of 23.30 indicate a high error. Real-world problems often require representing a single dependent variable using multiple independent variables. Therefore, we use a model called multiple linear regression to model these relationships. In this model, the weighted sum of m independent variables is shown as in the equation below. The solution to multiple linear regression is based on the least squares method, with the most popular being ordinary least squares abbreviated as OLS. Now, let us take a look at OLS. The goal of OLS is to find the weights in a multiple linear regression model that will minimize the sum of squares of the error terms. The equation that allows us to find the weights that obtain the least squared errors is as follows. Here, The X value is the matrix form of the input part of the dataset, which contains all the independent variables. Similarly, the D value is the matrix form of the output part of the dataset, which contains all the dependent values. Although there is no commonly accepted inventor of the least squares method, many mathematicians have developed this method in different contexts and times. The foundations of this method are based on the methods used to analyze observations in astronomy. In the 18th century, Carl Friedrich Gauss is generally considered one of the pioneers of the least squares method, as he used this method to calculate the orbits of the planets and made important contributions to this subject. However, when looking at written works, the French mathematician Adrien-Marie Legendre developed the least squares method before Gauss and published on the subject. For this reason, some sources show Legendre as the inventor of the least squares method. Linear regression is typically used to predict a continuous dependent variable, not for classification problems. However, theoretically, there is a way to use linear regression for classification. This method involves setting the dependent variable as class labels based on thresholding and then using these values for classification. Despite this, it is generally not recommended because linear regression is not optimized for classification problems, and its performance may be poor. Our goal here is to demonstrate that a problem can be mapped to another space using mathematical tricks and solved with different tools. For a two-class dataset, if the class labels are chosen as 0 and 1, using a threshold such as 0.5 is sufficient to convert a continuous value into discrete classes. If the calculated value is greater than the threshold, 1, otherwise 0, however, if there are more than two classes, a different approach may be required. Let's apply this with an example on the famous iris dataset. The iris dataset has 4 features, also called independent variables, and a dependent variable with 3 classes. Classification methods can easily learn two-class data. Therefore, we map dependent variables with more than 2 classes to 2-class labels with a 1 class versus all others perspective. We should also convert the D labels here into 3 different binary expressions with a similar perspective. The 1 class versus all others perspective requires us to transform the 3-class variable D into 3 different 2-class variables. This leaves us with 3 equations to solve. In the first equation labeled D1, we will try to solve the a class versus others problem. Similarly, in the equations labeled D2 and D3, we will deal with the B versus others and C vs others problems, respectively. Now, we have 3 multiple linear regression equations as below. According to these equations, we found their mean squared error values. Here, you see that the second MSE value is very bad. When the output values are calculated for each data sample using the linear regression equations with determined weights, the Y values in the table are calculated. In each row, the class representation that wins is determined with the biggest wins principle. In the first 2 rows, the first column values representing class A are greater than the other column values. Therefore, the regression equations trained for classification in the first 2 rows predicted class A without error. Similarly, the other rows are also completely correct. However, when the deviation value in the 4th row representing class B are examined, decision-making in this row was more challenging than in the other rows. This deviation caused the MSE value calculated for B to be poor. Nonlinear regression is used when the relationship between the dependent and independent variables is not linear. These types of regression models are used to model data more flexibly and can represent more complex relationships. Nonlinear regression allows for more accurate modeling of many real-world problems. There are many kinds of nonlinear model. Some of them are listed below. 1 exponential model, 2 power model, 3 saturation growth model, 4 polynomial model. Now we will see a manual calculation example. The question asks us to find the coefficients of multiple linear regression equation for the dataset given on the screen. At this point, I recommend you stop the video and do the calculations manually. Then you can continue and watch the solution. First, we should compute x transpose time x and x transpose time d. It is found in area marked with 1. The area marked with 2 shows how we found the weights using the Gauss elimination method. Finally, with the linear regression equation with these calculated weights, we can calculate success via MSE. Of course, R² and other metrics can also be calculated. Here, only MSE is calculated for the sake of simplicity. Thanks for watching. We recommend that you attend class for in-class activities.